All right, secondary educators, let's take a look at some of my favorite theorems in all of high school trigonometry, the law of sines and the law of cosines. We can't do either the law of sines or the law of cosines until we talk about how to find the area of a triangle without doing 1/2 base times height. So you've got your triangle ABC, nothing fancy here. The side opposite angle A is little a, and the side opposite angle B is little b, and the side opposite angle C is little c. And for the moment, let's focus here. And let's consider the height of the triangle. Well, the height is perpendicular to the base to which it is drawn. And so we know in this triangle, the sine of C is h over a, which means that the height of the triangle is a times the sine of C. So we normally think of the area of a triangle as 1/2 base height, but in this case, height is known. And that's where the familiar formula comes from. There's nothing fancy about picking angle C. So you get 1/2 AC sine B, you get 1/2 BC sine A. They're all the same. They all represent the area of the triangle, so we can do this construction as an altitude to any of the three sides. Okay? Once that piece is in place, once you can convince a teenager that that is true, then the next pieces fall into place very, very nicely. Let's take a look at the law of sines. The law of sines runs off the idea that there is only one area of a triangle, and that area of a triangle is 1/2 AB sine C, or if you like, 1/2 AC sine B, or if you like, 1/2 BC sine A. All of those are equal. The proof of the law of sines comes from the fact that A is not 0, B is not 0, C is not 0. So we can divide every fraction, well, we can divide every quantity by 1/2 ABC. And all of a sudden, the very familiar law of sines pops right out of there. It didn't fall from the sky. It wasn't given by divine revelation. It came by good math. Good math. Sine of an angle over its opposite side is sine of an angle over its opposite side is sine of an angle over its opposite side. But there's a little something missing, and I'd like to go for it if I can. You have your triangle ABC, and there's a circumcenter to that triangle. And that circumcenter is the center of a circle that passes through all three of the vertices of our triangle. And it's got some, oh golly, I'm so sorry. It's got some circumradius R, some circumradius R, some circumradius R. And how did we get the circumcenter to begin with? Well, we dropped perpendicular bisectors where this is A over 2 and this is A over 2, right? So what do we got? Now, here's where the mathematical sleight of hand, or should I say the mathemagical sleight of hand, happens. This is angle A. I argue that angle A also appears right there. This is an inscribed angle on arc BC. This is a central angle on arc BC. So the central angle is twice as big as its inscribed angle. And this altitude to an isosceles triangle bisects the angle from which it is drawn. Angle A is right here, which means that the sine of angle A, based on this triangle here, is opposite over hypotenuse. Which means that, with a little bit of algebra, 2r is A over sine A. And there's nothing fancy about using A. 2r is also B over sine B, and 2r is also C over sine C. And so the way the sine rule is written in some places is that A over sine A is B over sine B is C over sine C is twice the circumradius. And that argument is similar if the circumcenter is outside the triangle. You can make a similar argument that it holds true regardless of the kind of triangle you're dealing with. Okay, one other thing. Let's establish the law of cosines. There are lots of ways to establish the law of cosines. Here's one of them. We'll coordinatize the grid, and we're going to place triangle ABC so that its longest side is sitting on the positive x-axis. So we will perform whatever isometry is necessary so that the triangle lives in quadrant 1 with its longest side on the positive x-axis. So the coordinates of point B are A, comma 0. And the coordinates of point A are B times the cosine of C and B times the sine of C, because this is length B, and that's a rotation by C degrees. So what is C? Well, this little length right here, C is the square root of distance formula. B cosine C minus A squared plus B sine C minus 0 squared. Square both sides. Clean up the brackets. B squared cosine squared C plus A squared minus 2AB cosine C. And then this term gives us a B squared sine squared C. I think we know where this is going, right? I think we know where that's going. That's A squared. Cosine squared C plus sine squared C is 1. And then you get exactly what you want. That's the law of cosines. And it's called the law of cosines because it has a cosine in it. So again, the formulas come from somewhere. They were not delivered from above. They come from somewhere. And every teenager that you teach trigonometry to can understand this argument. They've seen the distance formula. They know how to use the unit circle. This is completely accessible to them. And so I hope that you will prove the law of sines and the law of cosines before you use it. My 8 minutes are up. Thanks for listening.